Okay, next victim across my workbench here is going to be my Sansui 4000. It definitely needs new caps. One of the dial lights burned out the other day, and of course it's 43 years old. It's entitled to need some TLC. I bought it for $15 at a Hamfest, as I've said in a previous video, and it's keeper. It's what I use when I'm not using something that I designed and built myself. Not to mention I haven't built any tuners, and the parts to do that are just almost unobtainium. So, I'll take a look at the top here, inside, my original label. Can't believe I only paid $15 for this thing. It's been a lot of fun. It did have some issues when I got it, and it needed some repair. It had been abused, without a doubt. Some nitwit put a 20 amp AC fuse in here, and I'll show that when I show the inside of it. Sorry, I'm going to be looking over kind of upside down here. And the fuse holder has been replaced. Those two fuse holders are not the same, the left and right. And I didn't do that. Alright, well, let's open it up. Let me get this thing on a tripod so you can see it getting opened up. Okay, here we go. Disassembly of the Sansui 4000 for some recapping. Slide the front out here, so get for having a messy workspace. That sounded loud. Alright. Now, look here. Again, some of the stuff in here isn't quite as neat as the Pioneer. Bit of dust. Get some spray air in here. We'll take a look at the inside of this too. We'll zoom in with the camera directly. Again, for 45 watts or 40 watts a channel, it's a very sizable power transformer by especially the standards these days. Everything's rated for about 1/10 of the out-rated power. We have a nice sizable heatsink. We have the original Sanken 2SD 213 output transistors, and they are they're 10 amp 100 watt devices. They have an FT of 8 megahertz and a current gain of 15 to 30 at 5 amps. Looking at the specs, it looks like something like a 2N3773 would be a replacement for them if they were to go bad. The new, and make sure you use the later Motorola or ON Semiconductor 2N3773. Eventually I'll explain more about that. Filter caps, output caps, or one of these are filter caps, these are the output caps. And we have the AM tuner, so 3 gang AM, and the FM. FMIF here. Perhaps the thing to do is to get the camera off the tripod. Closer look. Okay, here's the inside, the underside of the Sansui 4000. And like the Suzuki capacitor that's right here. Here's the emitter resistors for the power amplifier. And it's kind of interesting how they use the chassis as like a big ground plane. There. Okay, here we are inside of the Sansui 4000. And evidence of where the leads got burned off the transformer from some nitwit putting a 20 amp fuse in here. If something doesn't work, don't put a larger fuse in it. The bridge rectifier had apparently shorted. Transformer was very well made, has lugs inside of it. I was able to take it apart and actually replace the wires, and I used some nice Teflon insulated wire. And of course I replaced the bridge. And as I had mentioned earlier, the stereo decoder had a transistor go bad. And look at a couple things here. In the stereo decoder, there is a potential design issue. This transistor is the one I replaced that was bad. Don't know why. It's just bad. But this one right here, when it's in mono, it will have the emitter forced to the plus 25 volts through this resistor here, with only about 4 volts right here, and causing it to have a emitter base breakdown exceeded, which may cause it to, maybe not in this application, it may or may not cause a problem, but it'll cause it to become noisy and have really low gain eventually. So we'll look at that, and I'll probably put like an FDH 300 diode, low leakage diode, with the cathode to the base and the anode to the emitter to prevent that. And come down here and look at the power amp, and there's the bootstrap capacitor right by my finger right there. And problem is that the way that's designed is if when the output is swinging positive, the point where that 680 ohm and 4.7K meet is going to swing above the supply. Well, if there's not a low impedance source here, so will this node. So will this whole node, because if we look at the power supply, the only thing is the output of this 2SC627, and that's a slow start to keep it from going pow when you turn it on in the speakers. And that will cause the emitter base breakdown of this transistor. So we're going to look and see what's happening there with the scope in just a second. Okay, so we're going to drive this thing with a nice 400 hertz tone out here. It's 10 volts peak, 15 volts peak. Oops, not showing the screen. Trying to too many things at once here. So we're at 5, 10, 15, 20 volts, 40 volts peak to peak. Which is about 14.14 volts RMS. That would be about 25 watts into 8 ohms if I had a load connected. Alright, now that channel is a little bit more gain. Could just be where the balance control is. Now let's look what happens if put this carefully in here, And sure enough, that's the voltage at the emitter of that transistor. And of course I can't show DC. Maybe I can. Let's see, because it's 70 volts. Let's do DC. And it's hard to really see here, but so you have 20, 40, 65, and it's going up significantly there. So as you can see, it's a pretty significant voltage there. That's almost 15 volts. So yes, it is doing exactly what I was saying it was doing, and that will be putting reverse emitter base voltage on that transistor. Of course, if we only drive one channel, it'll be less, or we turn the volume down. Turn the volume down, of course. See, we're starting to get into that's before the emitter base breakdown. There, and they start to zener. And that is of the 2SC 627 right here in this power supply. So that's a design oops right there. And that will eventually cause that transistor to fail. It will get very low gain. Probably with music though, that's a pretty high listening level most of the time. Something like this, it has a pretty long life, but if you were jamming all the time with some inefficient speakers, it easily would cause this transistor to fail. And that leads me to another thing, actually. This one, the current gain selection in this is okay, so that it'll survive. But one thing to consider is, see this 10 ohm resistor right here? Is the base current drawn by this transistor multiplied by 10 ohms will be the voltage drop across it. If the base emitter voltage on this device, right here, the PNP, and the drop across this 10 ohm resistor is high enough, again, that can cause that same scenario to happen, in this case, to this driver transistor, which would be more fragile than the output. So we'll say that the amplifier was needing to put out, or the driver, in this case it doesn't need to drive this much current, but we'll say it had an amp. That would be 10 volts here. Then you have the drop across the bias string, so the current would be through the 100 ohm resistor, and then the Zener breakdown of this. The base of this transistor could, if there was no bias string, could be emitter could be 10 volts above the base, which is not good. But in this particular case, it would never really ever see more than maybe half an amp. So I think this one has a 4 volt breakdown, plus you've got a little extra help because there's voltage across the bias string here. You've got about 1.8 volts there, so you've got 5.8 before you're in trouble. So you're right on the line with this. Now, the same thing can happen to this device if the base emitter voltage of this transistor and the drop across this resistor is high enough, can cause this to have emitter base breakdown and cause it to fail. And this will be like a slow, painful death kind of fail. It might make the amp sound distorted, even though the devices may seem okay, because they've just become very low current gain after experiencing that kind of breakdown. I'll explain more about that in a later video. Maybe I'll get a whiteboard and draw some examples and actually take a transistor and force the breakdown and show you the current gain before and after at some point. Okay. Again here at the Sansui, here's the tone, control, and volume. Got the loudness tap. Leads to go over here. Switches for loudness. And what I'm going to do is I'm going to take out some of these caps. I have some of these values on hand. I'll replace. And let me test some of the others just to see how they do. See how this thing really is doing. One thing about this is that you'll see a video from the Pioneer SA9100 amplifier, is that since this is a single supply circuit, it biases the capacitors. There's significant DC voltage on them. And I can speak from experience, things that use the plus-minus supply and have coupling capacitors, a lot of times the caps that are in the signal path that have little to no bias, DC bias on them, are the ones that go bad. I'm not going to try to explain right now why that is, but from having serviced equipment in the past, now every time I see signal path caps that are polarized bad, it's always because they almost have no DC bias on them whatsoever. So there are some advantages to these old single supply circuits. Not to mention the fact that what's the point of the dual supply where you could do direct coupling if you don't? You've still got 100 coupling capacitors in the signal path. Not literally, but you get my point. Another view into the Sansui 4000. And what I want to do now is start recapping some of the other stuff. Use the power amp driver boards. And this is the input. Taking the shield off. Amp board. It's the RIAA equalization and some of the stereo separation for the tuner adjust on here as well. It's pretty interesting. I have the, get this to focus, original transistors, of course. Mitsubishi 2SC 871. And these two ELNA capacitors that are white, the schematic says that they're tantalum. But, so I don't know if they're bad or not. I usually haven't been very impressed with tantalum capacitors in the signal path, but this thing never sounded that bad. But I just know that it can reiterate its age of 43 years. That's way past the life expectancy of an electrolytic capacitor, used or not. So they're all going to get replaced. I'll see about these though. But I think it's really the serviceability of this thing. From working on some of the older Pioneer gear I've worked on, this is much more service friendly. And this is probably the beginning of the era of the Japanese going from making the cheap stuff like we associate now with made in China to much higher quality. So the stereo decoder, we'll pull that out a little bit, and it's in a socket too. The only ones that are not in sockets are some of the power supply stuff underneath, and of course the we have the AM board, and we of course have the FMIF right here. Okay, so we've got the electrolytics done. These tantalums, I'm not wild about tantalums in the audio path, but since they're not wet capacitors, and they seem okay, may just leave those alone. These are just some, before they made the lead-free ones, the Nichicon low leakage caps. They're 105 degrees C for one thing. I think they're 2,000 hours at 105 C, so they have a really long life. The other thing is, I've stated this before in another video, that I can't hear them in the signal path when I've done experiments. I prefer them over even the Muse, which I think is an improvement over a plain electrolytic. In the signal path, power supply, never really been able to discern much difference. But I would like to also point out that in doing this, I noticed a mistake in the schematic and from the manual. If you notice, my finger in view here, this 10 microfarad capacitor right here, the positive side actually goes to the emitter of this transistor, of the input transistor. And if we look here, we can actually see the switch, and it's in backwards in this part of the schematic as well. So not only is it in the wrong spot, the polarity is shown incorrect. So it takes its feedback after this capacitor, which is at DC. It's at 0 volts DC. So it has a whole 0.2 volts across that whoop-de-doo, but still, like to point that out.